In 2009, scientists working in a coal mine in Colombia pulled out a fossilized vertebra so large that at first they assumed it belonged to a dinosaur. It didn't, it belonged to a snake. A snake that, when they finally reconstructed its full size, turned out to be longer than a city bus and heavier than a small car. It wasn't an isolated bone either. Researchers eventually recovered enough vertebrae to map out the animal's full proportions, and the numbers kept getting harder to believe. This wasn't a myth, a movie monster, or an exaggerated legend passed down through generations. This was a real, documented species that actually existed. And compared to it, every snake alive today is a footnote. So, how did something that size ever exist? And more importantly, how did the planet ever produce conditions where a creature like that could not just survive but thrive at the very top of the food chain? The snake is called Titanoboa, and the numbers, once fully reconstructed, are difficult to process even when you're looking directly at them. Estimates put its length at around 13 meters, roughly 42 feet. For comparison, that's close to the length of a city bus. Its estimated weight comes in somewhere around 1,135 kilograms, or about 2,500 pounds. That's heavier than most small cars. At its thickest point, researchers calculated its body diameter at over a meter across, wide enough that an adult human would have struggled to wrap both arms fully around it. To put that in perspective, the largest snakes alive today, reticulated pythons and green anacondas, top out at roughly 6 to 9 meters and a few hundred kilograms at most. Titanoboa wasn't just bigger than those, it was in an entirely different size category. Modern snakes are large animals. Titanoboa was something closer to a force of nature wearing a snake's shape. But size alone doesn't explain why this thing could exist, because there's a hard biological limit that should have stopped a snake from ever getting this big. And for decades, scientists assumed that limit was absolute. Snakes are ectotherms, cold-blooded. Their body temperature, and therefore their metabolism, depends entirely on the temperature of their environment. This creates a problem as body size increases. Bigger bodies generate and retain more internal heat from basic biological processes: digestion, muscle activity, cellular metabolism. A massive cold-blooded animal living somewhere too hot would essentially cook itself from the inside, unable to dump excess heat fast enough to survive. This is exactly why modern tropical regions don't produce snakes anywhere near Titanoboa's size. The heat itself becomes the limiting factor, not food availability or predation. There's a calculated ceiling on how big a cold-blooded animal can get before its own body becomes a liability. So researchers ran the numbers backward. If Titanoboa existed at this exact size, what would the climate have needed to look like for that ceiling to be raised high enough to allow it? The answer reshaped how scientists understood an entire period of Earth's history. Titanoboa lived around 58 to 60 million years ago in the Paleocene epoch, a stretch of time right after the extinction event that wiped out the dinosaurs. Using the snake's calculated size as a kind of biological thermometer, researchers estimated that the tropical region where it lived needed an average annual temperature of around 30 to 34 degrees Celsius to support an animal that large. That's significantly hotter than the modern tropics average today. This was an unexpected discovery. At the time, the prevailing assumption was that global temperatures right after the dinosaur extinction were actually cooling, not warming. Titanoboa's fossil evidence pushed back against that assumption directly. A snake that large could only physically exist in a world running hotter than scientists had previously calculated, which meant the climate models for that era needed revising. In other words, this snake wasn't just a curiosity. It became actual physical evidence used to reconstruct the temperature of an ancient world that no thermometer was ever there to measure. But heat alone still doesn't fully explain it, because Titanoboa wasn't just big, it was apex. It sat at the very top of an ecosystem with essentially nothing above it. The site where its fossils were found also contained the remains of massive crocodile relatives and giant turtles, meaning Titanoboa shared its swamp with other genuinely enormous reptiles. And yet, based on its size and likely behavior, researchers believe it may have preyed on some of these other giants. A snake large enough to overpower a crocodile-sized animal in a direct confrontation simply through sheer mass and constriction force. Modern constrictor snakes kill through a method that sounds almost gentle compared to what it does to the body. They coil around prey and squeeze, not crushing bones in most cases, but tightening with each exhale the prey takes until the animal can no longer draw breath. Blood flow gets restricted. Organs shut down. It's quiet, mechanical, and absolute. Now scale that mechanism up to a body over 1,000 kilograms with muscle bands thick enough to wrap around prey the size of a small alligator. There would have been very few realistic escape options for anything it decided to target. So back to the question, could Titanoboa have swallowed something the size of a car? Functionally, no. Not a modern vehicle. Snakes don't have jaws built for rigid, non-deformable objects, and a car's shape and material would make it physically impossible, regardless of the snake's size. But in terms of raw mass and capability, Titanoboa was operating in the same weight class as a small car, and its actual prey, large fish, crocodilians, and other reptiles of substantial size, represented a comparable biological challenge. It wasn't swallowing vehicles, it was swallowing animals that, pound for pound, weren't far off. The comparison isn't really about the literal act, it's about recalibrating what your brain considers possible for a single living animal to be. Titanoboa eventually went extinct as the planet's climate shifted again, cooling toward conditions that could no longer support a reptile of that mass. The biological ceiling that the heat had temporarily lifted came back down, and animals that size became permanently impossible again under cooler global conditions, which raises an uncomfortable thought. The ceiling on size for cold-blooded animals isn't fixed. It's a direct function of the planet's temperature at any given moment. As global temperatures shift now, scientists studying reptile physiology have started asking what current warming trends could theoretically mean for cold-blooded animal size over very long timescales. Not within a human lifetime, but across the kind of deep time that produced something like Titanoboa in the first place. We tend to think of size limits in nature as fixed laws. Titanoboa is proof they're not laws. They're just the current setting on a planet that has changed its settings before and has plenty of time left to do it again.